All right, welcome back. We are now in week, what are we in, week 11 now? I think we're in the 11th week, so that would make this lecture number 21, I believe. And we are working now on chapter 17. The last two chapters, 15 and 16, were on correlation and regression. Correlation was how associated two different variables are linearly. And then regression was all about making the line that connects them. So now we have a further chapter that is on both correlation and regression, entitled More on Correlation and Regression. It's one of those chapters that you really don't have to guess what it entails. It's kind of obvious. So let's look at this scatter plot here. So if you ignore all the words on the page on the left, which we'll get to in a minute, if you just look at the scatter plot, would you say that there's a positive or a negative correlation if you look at all the dots that are scattered throughout the page? Would that be a positive or a negative correlation?
Positive.
Certainly it seems to be positive. And in fact, what we're going to show is that it has to be positive, even before we do any math. So let's look on the left. It says this scatter plot shows the scores of 37 students on the first and second tests of the semester. The axes have been located at the mean score for test 1, which was 73.6, and the mean score for test 2, which was 70.5. So those two lines, the horizontal line and the vertical line, are at the means of test 1 and test 2. So is the association linear? That is, do the points form an elliptical cloud? Like, they're not going to always fall on a line, but they basically form an ellipse either in one direction or the other. And I think we would agree that the answer to this is somewhat yes. I do see a moderate correlation. Do we all see what I'm talking about? You know, when you see the linearity, it kind of looks like there's certainly a line bottom left to top right. If it was weak, you would need a struggle to see a line if there was one there at all. If it's strong, it's obvious, and moderate is somewhere in between. So this seems to be somewhat moderate. What is the direction of the association? Well, it's positive. It's up to the right. And now consider the following. If you divide the scatter plot into 4 quadrants, much like we do with the x-axis and y-axis, which 2 quadrants have the majority of dots? First, second, third, fourth. First quadrant, top right. Second quadrant, top left, bottom right. 1, 2, 3, 4. Which 2 quadrants have the majority of points?
Top right, bottom left.
Do we agree with that?
Yeah.
Okay, well, if it's top right, bottom left, that certainly agrees with this positive association that we're seeing, that is going up and to the right. So the third question on the page, what percent of the students had either above average scores on both tests or below average scores on both tests? Of the 37 dots, how many of them are either both above average or both beneath average? So I just counted and I got my answer. If you're counting the upper right quadrant and the lower left quadrant, you're probably not doing this the most expeditiously. What's the easiest way to count how many dots fall in the top right or bottom left?
Count the ones that don't and then subtract.
I'm sorry?
Count the ones that don't fall in either of those quadrants and then subtract.
Exactly.
The total.
Right. We know there's 37 total. How many of them do not fall in either in the first top right or bottom left?
8.
8. So how many of them do?
29.
29. So 29 over 37, that's roughly 78%. 78% fall either top right or bottom left. Right? Now, if the association is positive, like we believe it is, then points with X values above average tend to have Y values that are blank average. What do you think that number is? Or what do you think that word is? If it's positive, points with X values above average tend to have Y values that are. What do you think? Anyone? If the association is positive, points with X values above average tend to have Y values that are. Anyone? Anyone? Is anyone there? And the answer is, well, Sabina said below average. If it's positive association, then when X is above average, is Y below average, or is Y going to be above average more likely?
Above.
Above. We want positive right, correct? She corrected herself and she smiled, so it makes it all better. Now, points with X values that are below average tend to have Y values that are. Sabina, you got this? I have faith in you. Oh, someone just said it. What was the answer? Oh, man.
Below.
Below. Yeah. That's an epic fail right there. But you smiled, so it makes it all okay. I gotcha. My life's an off life, so I totally understand. So again, if the X values are above average, so are the Y values. And if the X values are below average, so are the Y values. That's positive association. Above, below. So draw horizontal and vertical lines at the proximate locations of X bar and Y bar on each of these scatter plots. Let's do the right one first, because I think it's a little easier. Where would you say is the X bar? The average of the X's. If we ignore all Y association, just look at the X's. In other words, if you imagine these dots just kind of dropping and forming a regular dot plot, where would the average be located roughly? For the one on the right, where's the X average?
A little to the right of the center.
Okay, so about there, give or take.
Give or take.
Give or take, but it doesn't gotta be perfect. Give or take is fine. And where would the Y average be? If all of these dots moved to the left and formed a dot plot along the Y axis, where would the average be roughly?
In the center again, roughly.
Okay, so roughly here.
Yeah.
Okay, so would you say based upon this that we have positive or negative association?
Positive.
Positive, because the majority of them are above or below.
Mhm.
Now, if we did the same thing here for the X's and the Y's, the X's here kind of look maybe a little bit to the right. And the Y's seem to be a little bit on the bottom. Let's see, is that correct? What do you guys think? What do you think the Y one would be? Seem to be more on the bottom than on the top. Something like this.
Yeah, I would say about that.
Okay. So here it's clearly the majority of them are top right, bottom left. We have positive association. But here, none of the four quadrants really look like they have the majority of them, which makes sense because when you looked at this graph in the first place, it's really hard to see any linearity at all, right? It's more like a blob of points than there is a line, at least to me. So the stronger the positive association, the more likely it is for the points to be above or below. And of course, if the association is negative, it would be above, below, and below above. Whereas if it's weak or neither, if it's nonlinear at all, then they're just kind of like all over the place and you really don't see anything. Does that make sense?
So then that statement would be true.
If the association is negative, points with X values above average tend to have Y values that are below average. And points with X values that are below average tend to have Y values that are above average. That is true for a negative association graph. If it's nonlinear, if there's no linearity at all, then the points are going to be all over the place and they're not going to be more likely to be above, above, below, below, or above, below, below, above. Does that make sense?
Yeah.
Okay. So here is the actual formula for the correlation. The calculator does it for us automatically, which is really nice. Okay. But the formula says as follows. First, they're defining the letter that we use for correlation, which the calculator uses as R. No problem there. We do 1 over n minus 1. N is number of points. If you only have 1 point, then this formula makes no sense, but nor should it make sense. If you only have 1 point, then there's really no way to gauge any connection between the two variables, right? You have 1 point, tells you nothing. So you need n to be at least 2, which makes sense. So you do 1 over n minus 1. What does this symbol here tell you to do? I kind of forgot. It's been so long. What is that symbol? Have we seen that symbol before?
I am blanking right now.
So someone said it's summation to add them. That is correct. What are we adding? We're adding these. In other words, you got to find X bar, the average of the X's. You have to find SX, the standard deviation of the X's. Same thing for Y bar and SY. And then do X minus X bar over SX, Y minus Y bar over SY for every single point. So every point gives you a number. And then we add all those numbers together. By the way, what are these called? X minus X bar over SX and Y minus Y bar over SY. We've given names for these before. Do you guys remember these? What these are called? Your data minus the mean divided by the standard deviation. Do you guys recall those? We've had them before. Data minus mean over standard deviation. What are those?
Is it with an R?
No, it is with a. Well, if I give the letter, it kind of gives it away.
Someone said it already.
It's a Z-score. That's right. If I said it's with a Z, I kind of felt that would have given too much. But those are my Z-scores. So if X is above average, then what can you tell me about whether this is positive or negative? If X is above average, then what is this value going to be, positive or negative?
Positive.
Positive. If X is above average, then X minus X bar is a positive number. SX is always a positive number, so this is positive. If X is below average, then X minus X bar over SX is what?
Negative.
Negative. If Y is above average, then what is this?
Positive.
Positive. And what if Y is below average?
Negative.
So it makes sense why, if there's lots of dots here and here, the correlation is positive, because if you're a dot here, then both your X minus X bar over SX and Y minus Y bar over SY, they're both positive numbers. And if you multiply two positive numbers, what do you get?
Positive.
Okay, what about down here where they're both negative?
Positive.
So here and here, you're adding lots and lots and lots of positive numbers. Whereas here and here, you'd be, oh, what the hell is that? Here and here, you'd be adding lots of negative numbers. So negative association, here and here, add lots of negative numbers. give you a negative correlation. Here and here, add lots of positive numbers. That's why we have a positive correlation. Does that make sense a little bit?
Yeah.
Yeah.
Okay. And in fact, this is what I just said. When X and Y are both above average, the product is positive. When X and Y are both below average, the product is positive. So for a positive association, most of the terms will be positive. So R should be positive. Exactly what I just said. If X is above average and Y is below average, so we're in here, the product will be negative. When X is below average and Y is above average, the product again will be negative. So most of the terms will be negative, and therefore R should be negative. Of course, if the association between X and Y is very weak, then there should be about the same number of terms which is positive and which is negatives. So for a weak association, R will be close to what? If a bunch of them are positive and a bunch of them are negative, when you add them all together, R will be close to what number?
Is it 0?
It is 0, right? If lots of them are positive, we expect a positive number. If most of them are negative, we expect a negative number. But if we have the same amount that's positive and negatives, and they're all over the place, then we would expect when you add them to get something close to 0. Now, that's about R, lots of R, everything's about R. But now the question is, what about R squared? Because if you look at your calculator, when it gives you your final answer, it doesn't just give you R, it also gives you R squared. So what is R squared? Okay, well, first of all, the closer R is to 1 or -1, we know the stronger the association between the two variables. Correct?
Correct.
Okay. When R is exactly 1, they fall on a line in the positive direction. When R is exactly -1, they fall on a line in the negative direction. And when R is 0, then there's complete blob of points with no linearity at all. But R equals 0.5, 0.6, 0.7, like what exactly do those mean? What's a physical interpretation of the exact value? So there is none. There is no physical interpretation of R, but there is a physical interpretation of R squared. And it's actually a pretty important one, which is why I'm doing this chapter. If I didn't have R squared, I wouldn't even do this chapter. So, example. There's a lot of variability in course grades. How well can we predict a student's grade from the number of times the student was absent? Well, we can make a scatter plot, and we have absences on the horizontal axis because that's the explanatory variable and the grade on the vertical axis. And we see that sure enough, not a lot of absences, high grades, lots of absences, low grades. Seems like a reasonable association. And when we actually do the scatter plot, we get an R value of -0.8. Negative sign makes sense because it's heading downwards. And it's telling us that the correlation is -0.8. Now, do all the Y values, are all the course grades for this example exactly the same? Did everyone get exactly the same course grade?
No.
And give me a reason why not. Why didn't they all get the same course grade?
Not everyone has the same mind.
I'm sorry?
Not everyone has the same mind.
Okay, not everyone has the same minds. In other words, some are smarter than others, or at least more inclined for that particular subject than others. What are some other reasons why they might not get the same course grade?
Different grades on different assignments.
Absences.
Well, okay, absences should certainly be a factor, because as we can see here, there's a pretty strong correlation between absences and grades, right? Right? certainly it seems like there's a strong correlation. Negative 0.8, that's a pretty strong correlation. But look at these three. These three had the same number of absences, and they didn't get the same grade. And these two, same number of absences, and didn't get the same grade. So obviously, absences alone can't be the only reason why people get the grade that they do. In fact, there was already the choice, or already the other answer. Different minds. They might study different amounts. They might have different grades on different papers. Maybe they study the different things. You ever study for a test and it's like, oh my God, everything I studied wasn't even on that test. Versus someone else might have studied exactly the right things to do well. There's lots of reasons why people's grades are going to be different, but our study here only takes into account one of those reasons. What's the only reason that our study is studying as to why people get different grades? This particular study only looks at one factor, which is what factor?
Absences.
Absences. But there are other factors that we're not considering. So part of the reason people get their grades they do is because of absences, and part of the reason they get the grade they do is for the other stuff that we're not considering. Wouldn't it be nice if I could put a number on what percent of the reason why the grades change is because of absences, and what percent of the reason why the grades change goes to everything else that I'm not considering? And the answer is yes, I can. And it's the R squared value. If R is negative 0.8, what's the R squared value for this example?
.64.
0.64, which other percent is what?
64.
64%. So 64% of the reason why the grades change is due to absences, and 36% of the reason why the grades change is because of everything that we're not focusing on. So the R squared value is the percentage of the variation in your Y value that the data suggests is caused by the variation in your X value. Whereas all the other reasons out there amount to the other, in this case, 36%. Okay? Does that make sense? Does that, I'm not telling you how we know this or why it's true, but does that sentence make sense what I said? That the R squared value tells you the percentage of the reason why grades change because of absences as opposed to all the other things?
Yeah.
Okay, that is what the R squared value measures. What percent of the variation in your grades is caused by the variation in your absences? So in this example, we have the actual data. Absences 0, 0, 0, 1, 1, 2, 4, 7, and 12. And here are their course grades. So they did most of these things for us. Deviation from the mean. Well, they calculated the mean for us, which was so nice of them. 74. So 90 minus 74, 16. 97 minus 74, 23. 83 minus 74, 9, and so on. They didn't do it all for us. They left one blank. So let's fill it out. What number should go here?
4.
4. And then they took all these numbers and they squared them all. And they get all these numbers. What number goes here?
16.
16. And then they added that whole column. So I'll take out my calculator. 256 plus 529 plus 81 plus 361 plus 196 plus 1 plus 16 plus 256 plus 1024. And I get 2720. And this is the TSS, the total sum of squares. The TSS, total sum of squares. It gives me 2720. Now, we also have the line of best fit. And the line of best fit, if we go back up there, was 84.8 minus 3.6x. 84.8 minus 3.6x. 84.8 minus 84.8 minus 3.6x. That's the line of best fit. So we have the predicted value when x is 0. It's just 84.8 and 0, 84.8 and 0, 84.8 and 1 and 1 and 2 and 4. Oh, they didn't do that for us. What is the predicted value when x is 4?
$70.4.
70.4, which means that there's a boo-boo on this page. Anyone see where the ouchie is?
Would it be that 7 has the same number of?
Yeah, this can't be right because 4 is 70.4. So what should 7 be?
I got 59.6.
Uh-oh, do I have a new boo-boo?
Yeah.
What's the new one?
The one below.
Number 4, the one below also must be wrong. What should that be? Anyone? Anyone there?
Yes, I'm having a little trouble. How are you getting these numbers?
Oh, here is a formula.
Okay.
Just plug in X.
Oh,
The predicted value comes from the line of best fit.
41.6.
41.6. So let's go ahead now and make sure the residuals are all correct. Because remember what the residual is. It's the actual value minus the predicted value. 90 minus 84.8, 5.2, that's good. 97 minus 84.8, 12.2, that's good. 83 minus this, that's good. 55 minus this, that's good. 88 minus this, that's good. 75, 78 minus 70.4, what's that?
7.6.
So that should be a 7.6 residual. Next, 58 minus 59.6.
that's right.
1.6.
Good, and then 42 minus, yeah, these are good. So these are wrong, but luckily these numbers are correct. And that's what we use in these. Okay, because then what do? We take these numbers and we square them. 5.2 squared, for example, 12.2 squared, negative 1.8 squared, 26.2 squared, 6.8 squared, 2.6 squared, 7.6 squared is how much?
57.76.
All right, so I'm just going to do 57.8 like them. Even though my calculator, I'm going to keep it 1.6 squared and 0.4 squared. And then I'm gonna go ahead, I'm gonna add all these numbers. So that plus, and I'm gonna do my calculator because on my calculator, I have a few more decimals than they do. I don't know why they round. There's really no reason to. These numbers are pretty small. 38.6. Actually, this one doesn't even close. 6.8 squared is 46.2. There are lots of mistakes here. Whatever. 27 plus 148.8 plus 3.2 plus 686.4 plus, well, let's try this one more time. 5.2 squared plus 12.2 squared plus 1.8 squared plus 26.2 squared plus 6.8 squared plus 2.6 squared plus 7.6 squared plus 1.6 squared plus 0.4 squared gives me 979.04. 979.04. And what is 979.04 divided by 2720? What do you get for that?
0.36.
36%. In other words, the sum of the squared residuals, SSR, sum of the squared residuals, divided by the total sum of squares, TSS, gives you not R squared, but rather what? SSR over TSS gives you what? We know R squared is 64%. This is not 64%. It's 1 minus 64%. So this formula here connects the sum of the squared residuals divided by the total sum of squares to R squared. Fair not, you will need to do this by hands, but you should still know what went down here. So are there questions on this?
No.
Okay. Okay. So the total sum of squares at TSS is part of the calculation due to the standard deviation of the grades. It measures the variability in the grades, right? It's all about the grades. Okay, the grades, their average, how far away, you square them all. It's all about that. Nothing about predictions, nothing about residuals, nothing about best fit line. It's all about the actual scores. The sum of squared residuals, on the other hand, measures how much variability remains unaccounted for after using the number of absences to predict the grades with the least square regression line. So this divided by this is what is unaccounted for by the regression. It's the other 36%. So it's 1 minus the part that is accounted for, which of course is R squared. Does that make sense? Hopefully it does. Hopefully it does. In fact, take a look at this. Here are the grades themselves. The grades themselves spanned, as you can see in the grades, we had a 42 to a 90. So if I make a dot plot of the grades, they're kind of everywhere from 42 to 90 as such. This is their dot plot. If I do the residuals, on the other hand, these numbers here, most of the residuals are pretty small, in fact. So if I do a dot plot of the residuals, most of them are near 0. Yes, there's one guy out here, but for the most part, most of the residuals are near 0, correct?
Yeah.
Yeah, okay. So the variability of the residuals is relatively small compared to the variability of the grades themselves. right? Yes, no, maybe so.
Yes. Yeah.
Okay, so this is some deeper stuff, and I have this book here that I grabbed off the shelf yesterday to look through. It's a little more advanced book on statistics that I use when I teach the 300 level stats, but they go much deeper into this stuff. And it's really, this book's a little better than the one that we use because, I mean, obviously we're just using PowerPoints. The PowerPoints kind of just give you facts, but they don't really explain why the facts are true. And you're not really expected to know necessarily why the facts are true because you're going to be middle school teachers or maybe high school teachers, probably middle school teachers. And the math that you do, the students are not necessarily going to be ready to ask some of the deeper questions. But ideally, you have the answers to those deeper questions. Just it gives you a deeper understanding of what's going on. So, if any of you are really sufficiently interested in going out and enhancing your understanding of statistics, you're more than welcome to message me. I'll give you some good books that you can use. And if not, that's okay too. We're going to skip this one only because, actually we can do this one. Suppose all the points in a scatter plot fell exactly on a line. What would the value of R be if all points in the scatter plot fell exactly on a line? If all the points fell on a line, what would R be?
1.
1. Or, actually, there's two answers. 1 or what?
-1.
1 or -1, depending if the line's going up or down. Of course, if the line's flat, it would be 0. So technically, it could be 0 as well. But let's ignore this one just for the sake of this particular discussion. What would the value of R squared be in both of those examples? If R is 1 or -1, what would R squared be?
1.
It would be 1. And therefore, if I made a dot plot of the residuals, what would the dot plot look like if all the points fell on the line? What would the dot plot of the residuals look like?
Wouldn't it just be 1 dot?
Well, every point would have a dot, but they'd all be at 0
Oh, yeah. Okay.
because every one of the residuals would be 0 because every one of the predictions is the same as the actual value. So therefore, value minus predicted value will be 0. They'd all be at the same spot. So the value of the, they call it the RSS, but it's really the SS. Who wrote this? Anyways. The sum of the squared residuals, SSR. What would the value of the sum of the squared residuals be if each one itself was 0?
0.
0. So if I do the SSR over the TSS, what would I get?
1.
Try again.
0.
You get 0, which is the same thing as 1 minus R squared. So what would R squared be?
1.
Well, it's still 1, hasn't changed from the beginning. All right, so this just reinforces why it should be 1 in this particular example. Nothing new, just a reinforcement. Okay, example. So the term regression was coined by Sir Francis Galton in the late 1800s. Galton was the first person to investigate human heredity statistically. Here's a 21st century version of some of what he studied. So we have lots and lots of data of fathers and sons when it comes to their height. The mean of the father's heights was 69.4 inches, and the mean of the son's heights was 69.4 inches, both of which had a standard deviation of 3 inches and an R value of 0.5. When you look at that scatter plot, does it look like it's going up to the right or down to the right? Up to the right or down to the right?
Up to the right.
Up to the right, which means we expect some positive correlation here, correct? In fact, R is 0.5, as we already saw. The regression line is y hat equals 0.5x plus 34.7. So, if you are a male, use that equation to predict the height of any sons that you might have. And if you are female, use this equation to predict the height of any daughters that you might have. So I'm going to do it for myself, see how tall my kids are going to be. If I'm ever unlucky enough to have one, so 0.5 times, let's see, 12, how tall? Okay. Okay, so basically, if I ever had any children, boys, they would be very, very close to my height. Now, what percentage of the son's height can be attributed to the father's height versus other factors that are not being considered? What percentage of the son's heights, the variability in the son's heights, can be explained by variability in the father's heights? I'm looking for an actual number here. What percent of the variability in father's heights in father's heights predicts variability in son's heights? This is like the entire lesson for today. Anyone? Please give me some validation as an instructor. Someone help me out here. What percent of the variation in son's heights can be explained by variation in father's heights? Should be a very simple calculation. Is anyone even there?
Yeah, we're here.
Well, you're here. Is anyone else here?
I'm here. Hi.
Hi. So, can someone just throw out a guess as to what percentage of the variation?
Is it 25%?
25%, just R squared. Take 0.5 and you square it. What's 0.5 squared?
0.25.
That's it, 0.25. That's the entire lesson was today. It was R squared. R squared is the percentage of the variation in the Y values that can be explained by the X values. 25% of the reason of the explanation behind son's heights can be attributed to the father's heights, which leaves how much to other factors?
75.
75%. Would you say that father's heights is a large factor in son's heights?
Not really.
Well, 25% might still be a pretty large amount. But what are some other things that might be contributing factors as well?
Mother's height, diet,
Mother's heights,
diet,
diets, grandparents' heights, certainly, or uncles, aunts. Basically, there's probably a lot of genetic code just going on there overall. That's certainly not my field, but I can imagine that there's, stuff in the genetics beyond just, simple, oh, okay, well, mother, father, boom, here's everything you need to know about your child. Diet, nutrition, maybe what the mother does while pregnant. I don't know. There could be lots of things, lots of reasons why. So maybe 25% as a single reason might be the most contributing factor because everything else might be 5%. I don't know. But the fact of the matter is it's only 25%. And other factors are going to play a huge role. Okay, with me so far?
Yeah.
Okay, so now the regression line itself has this formula. Up until now, we haven't worried about the formula. We just used the calculator to get it. How does the calculator get it? Well, this is the formula that the calculator uses. It computes X bar, it computes Y bar, it computes SX and SY, it computes R. It throws everything into this formula, and out pops the answer. Y hat equals Y bar plus R SY over SX times X minus X bar. This is the formula of the best fit line. And it seems very similar to the point slope form. Y equals Y1 plus MX minus X1. A very, very similar form. In fact, it's exactly the same. The slope of the best fit line is RSY over SX. That's the M part. Where X bar, Y bar just happens to be some point on the line itself. And in fact, here is the scores of a group of students on 2 tests. Here are the information, pretty strong R value. So the question is, what is the equation of the best fit line? Let's start by finding, well, the only thing we need is your slope because we have Y bar already. So let's go ahead and do it. Y hat, which is the predicted Y value, equals Y bar. What's Y bar here? And they give me lots of information here. What's Y bar?
$70.5.
70.5, because test 2 is your Y value. So 70.5 plus, what's the slope? What's the slope? We have R, SY, and SX. We can just plug it all in. Whatever, 0.808 times X minus X bar, which is 73.6. So what does the regression line predict? That a student who gets a 40 on the first test will get on the second test. How would I go ahead and predict that?
Do you plug 40 into the equation?
Exactly what you do. So when you do that, what do you get?
43.35.
43.35. Excellent. So what is the regression effect? Many people would expect that a man's sons would grow up to be about as tall as he is on average, and that a woman's daughters would grow up to be about as tall as she is again on average. What is the reality? Well, let's take a look. Use the regression equation to predict the height of the son of a man who is 6 inches taller than average. Well, if he's 6 inches taller than average, what is average again for men, according to the formulas above? Let's test 1, test 2. What is average for men?
69.4.
69.4. So if they're 6 inches taller than average, then how tall are they?
75.
75.4. Yeah.
75.4. And if you plug 75.4 into the formula and compute, what do you get?
$72.4.
72.4. So you're actually get closer to the average than stay where you are. And what if you were 6 inches shorter than average and you had a child? What would that child's height be? Well, first, what is 6 inches shorter than average?
Be 63.4.
3.4. And how tall would their child be on average?
$66.4.
So again, whether it's shorter or taller, and I'll see someone's in the chat, maybe that was the answer. Yeah, to be honest, I see that. So whether you're taller or shorter, your child will be closer to the average than you, on average. So this is the regression effect, that we tend to regress. We tend to move over time toward the average. If we're above average, then our offsprings will be towards the average. They'll go smaller, shorter, and if we're below average, they tend to get larger. This is the regression effect, which is why it's called a line of regression, because it's, was used to study regression historically. So we can skip this. Okay, so what is the regression effect? Suppose that you have two measurements for each individual. For example, the scores in the first midterm and the second. Okay, if we convert each of the two test set of scores to z-scores, the individuals with the lowest z-score in the midterm will tend to do better on the final, and the highest scores in the midterm will tend to do worse on the final. As a general average, we tend to regress toward the average. This is the regression effect. Now, that's only if it's completely done at random. Obviously, test scores are not by random. People who tend to score better on the first test study harder, prepare better, pay attention more, whatever the case may be. So it's not just random chance. If it was complete random chance, then for every good score that you get a bad score. That's not really the way it occurs. But for genetics, for the most part, it is random chance. You don't have really any say. You can't prepare your child to have a certain height. It's just whatever comes out, comes out. That's just the case may be. Okay. So in what ways does your score on the final exam reflect some element of chance? Well, you don't always know what questions you're going to be asked, what to study for. There still is chance involved on every exam. Maybe you study every other chapter and either you get amazingly lucky or amazingly unlucky, or the things that you don't know very well, he didn't ask, she didn't ask, or amazingly enough, everything I didn't know, she did ask. There still is some luck involved on these exams. So there's always going to be some motion of grades, even though the part that's not luck will keep you somewhat in the right vicinity, but the part of luck will have you move towards the mean. That is the regression effect. Does that make sense?
Yeah.
I hope so. Okay. We're not going to do this because it's just too difficult. Over the phone. I mean, not over the phone, over the computer and whatnot. So that takes us to the end of chapter 17. So we're going to stop here. I'm not going to start a new chapter with 10 minutes to go, but 17 is done. Have a good Veterans Day break. And I will see you all a week from today to start chapter 18 and beyond.